So, the law of conservation of energy. It should be echoes and rumbles. This is really, really important. This is fundamental to the universe. In fact, this is fundamental enough that if we meet something that doesn't work for this law, we'll change our observations rather than rewrite the law. And I'll tell you a story about how that worked a bit later. In general, we're going to start out. A force in the same direction as motion, like force 1 below, does positive work. A force opposite to the direction of motion, friction, does negative work. It bleeds off energy. A force in the same direction as you're moving adds energy to the system. A force in the opposite direction bleeds off energy. So, although work can be positive or negative, please remember it is not a vector, it's a scalar. It has no direction. What does negative work mean? Justin, negative work means the object is losing energy. And now I can give you our formal definition of energy. Energy is the ability to do work. And what was work? Work was equal to what times what? Force times distance. So if you have energy, if an object has energy, it has the ability to apply a force over a distance. It's got the ability to do work. There are many types of energy. We're just going to look at a few. First is the energy of motion. Now we call that kinetic energy. So Justin, since you were late, if I were to throw this tennis ball, but instead of a tennis ball, let's imagine it's a baseball, and I hit you in the face with it. When it hit your face, would it apply a force over a distance? Would it do work? If a baseball hit you in the face, would it apply a force over a distance? Would it do work? Say yes. It would dent your face. It would apply a force. It would bend your face in over a distance. It would do work. Okay? So if this was moving and I threw it at you, I'm not gonna, and I threw it at you. When it hit you, would it do work? Say yes. So does it have energy? Say yes. Because energy is the ability to do work. Anything that's moving has kinetic energy. Kinetic energy is the energy of motion. Okay? Oh, and the faster you're moving, the more kinetic energy you have. Oh, and it was instead of a baseball, this was a bowling ball. Would it do more work when it hit you in the face? Yeah. The heavier you are, the more kinetic energy you have. This is going to explain a lot of football in a bit. Another type of energy is heat. What's most heat created by? Which force begins with the letter F? Yeah. Then we have gravitational potential energy. Now, potential means stored energy. Gravitational potential energy is stored energy due to an object's height. Once again, people on YouTube are wondering what's going on. If I were to drop this and it hit Justin, would it do work? Would it apply a force over a distance? Yes. So does this have stored energy? Okay, you ready? More energy or less energy now? More. So one thing gravitational potential energy depends on is height. What if I did this with a ping pong ball? Would Justin even be worried at all? So what else does stored energy depend on? Not just your height, but your, what's the difference between a ping pong ball and this? Mass. I gotta be fussy. Mass. Weight is the force in mass. Weight is the force in newtons. Boy. Don't worry, I've never dropped it yet. Someday. Okay. So potential energy, that's the fancy word for stored. Chemical potential energy, like gunpowder. There's energy stored in gunpowder. Chemical potential energy, like in the food that you eat. That's why you have to eat food. Your body needs to get its energy from somewhere. And so there's chemical potential energy stored in food, especially in sugars. Other forms, sound energy. Sound is a form of energy. Elastic energy. In fact, elastic energy is a great example of potential energy because, do I have a rubber band here? I used to have a rubber band here. When you pull a rubber band, you're storing energy as potential. When you let it go, you can do work with it, often turn it into kinetic. You've all fired a rubber band at somebody, right? Should have had one ready. Nuclear energy. That's the energy stored inside the nucleus of an atom that we can release when we make atom bombs and nuclear reactors. In this course, and many others. In this course, we're going to look at what's called mechanical energy, which is broken down into two main types. Kinetic, because we've been having stuff moving with velocities and accelerations and things. So we're going to look an awful lot at the energy of motion. And potential, stored. Especially gravitational potential energy. In fact, unless I say different, if I just say potential energy, you can assume I'm talking about gravitational potential energy. We're going to be using it very often. Oh, and I should say, this explains negative work. When you do negative work on an object, what that really means is that the object is losing energy. So, looking at this weight, right now I'm doing positive work, negative work, because it just lost energy, it's not as high, it won't do as much damage if it hits the ground. Is that okay? Believe it or not, Kyle, that explains an awful lot if we combine it with one more thing. First, let's give you some equations. Gravitational potential energy. This is the work that you have to do against gravity in order to change an object's height. Equation. My symbol for gravitational potential energy is this. Capital P, capital E. Standing for potential energy. Sometimes you'll see it E with a little p, and that's actually the proper symbol. The only problem is in Physics 12, there is a unit where E means electric field and E means energy and E means something else, and kids get them confused. So I decided, even though it's technically wrong to use two letters, P and E, for one thing, I'm going to do it. Equals, well, energy is the ability to do what? So let's start out with saying it's force times distance. Noah, when you're lifting something, which force are you doing work against? So here it is. The equation for potential stored energy is, what was the equation for the force of gravity? What? You had it before? mg. And what we're going to say, since it's a vertical distance, instead of using distance, we're going to use a word that begins with the letter h. Height. Here it is. You want to know how much energy you're storing in an object when you lift it up? It's mgh. We kind of have seen this one. I snuck this in whenever we looked at stairs and things in the work lesson, but there it is. Potential energy is mgh. Spencer has a mass of 75.4 kilograms. I don't think that's you. I think it's a different Spencer. Natalia, what's the first thing asking me to find? Mass or weight? Weight. Okay. Because I was on you a little bit. Oh, when they ask for weight, what's that? What's weight another word or a synonym for? Don't say kilograms. Don't say mass. I've been... Newtons, but which force? mg. Right? When I say weight, what I really mean is that. Okay, so what's his weight? Weight is a synonym for the force of gravity. And yeah, Carson, you're right. It's in newtons. mg. It's going to be 75.4. Noah, what's g? Yep. You had this the other day. I knew you'd get it back. I know. First thing in the morning. Which is what? By the way, I'm lazy. If you're ever trying to calculate this in your head, instead of 9.8, what's a nice number close to 9.8 that's really easy to do math with? 10. I actually try and crunch numbers when I'm standing in line on amusement park rides, figuring out how many fourths. Anyways, what do you get? 75.4 times 9.8 is what? Someone. 738. I'll go 0.9. You know what? I'll go 700, Mr. Duke? 739. Is that right to three sig figs? 730.9, okay. Units, newtons. So, when Spencer jumps, he can raise his center of mass 75 centimeters from the ground. You wish. At the top of his jump, how much potential energy does he possess? What does this question want me to find? Potential energy. And that's going to be mgh. What's mg? Now, we just crunched it, but I'll write it out again. It's going to be 75.4 times 9.8. If you already have that number on your calculator, all you need to do is multiply by h. What am I going to multiply by 75? No, because what are the units next to the 75? So meters is what? 0.75? How many joules of energy does it take for Spencer to jump that high? $554.2. And basically what the law of conservation of energy says is that energy's got to come from somewhere. You can't magically get energy from nothing. So I asked, where did that energy come from? When you exercise, where does your energy come from? Magic? Witchcraft? No. Food. And you've noticed if you're into athletics at all, in the past 15 years, an entire sports science has evolved on teaching athletes to nourish themselves properly. The saying is this: good nutrition can't make you a better athlete, but bad nutrition can sure make you a worse athlete. Okay? It's got to come from somewhere. Food. So that's gravitational potential energy. The second type is kinetic energy. Kinetic energy is the energy of motion. As an equation, I use KE for kinetic energy. Again, you'll see some textbooks use E with a little K, and that's also fine. Do you remember what I said it depends on, Justin, when we imagine me throwing this tennis ball at your face? What would hurt more, faster or slower? Okay, so it's going to depend on velocity or speed. What would hurt more, ping pong ball or bowling ball? So it depends on mass. The actual equation is this: a half mv squared. And I'm not going to derive it. We'll derive it in physics 12. So love the little derivation, actually. It's a half mv squared. Where does the half come from? It comes out of physics 12. Or maybe I derive it later on. I can't remember. But I know I derive it in Physics 12. You want to know how much kinetic energy an object has? 0.5 times its mass times its... Oh, by the way, did I put a vector bar above the V, or did I leave it? Speed, because energy is also a scalar. And that's going to be hugely useful. Squared. A .357 Magnum bullet weighs 8.1 grams. I looked it up. Travels at 490 meters per second. I looked that up too. How much kinetic energy does it possess? Are bullets moving? Okay. Half mv squared. 0.5. Oh, can I use 8.1? What are the units next to the 8.1? Grams. Do I do math with grams? Nope. Okay. 8.1 is grams. How many kilograms? Be very careful. How many kilograms? That's 810 grams. Because kilo is out of 1,000. So kilogram is 1,000 grams. In other words, it's divide by 1,000, 0.0081. And I'm glad you did that. That's the most common mistake kids make. Is my speed in meters per second? Yes? Okay. 490 squared. And believe it or not, the two things that I've just showed you explain most of sports in terms of coaching and science. What do you get? 0.5 times 0.0081 times 490 squared. 972 joules of energy. About 1,000. Is that okay? So let's put it all together. We have many types of energy. The two we're going to be looking at the most, Oscar, are potential, in particular gravitational potential, mgh, and kinetic, the energy of motion, half mv squared. The law of conservation of energy, G, says this. First of all, I'll give you the formal, and then I'll give you the easier way to remember it. Energy is neither created nor destroyed. You can only transform it from one type to another. This means if we are looking at a closed system where there's no outside sources of energy, you don't have a motor in the system, it's not plugged in to something, you don't have a battery hooked up. If you're looking at a closed system, the total amount of energy at the start and the total amount of energy at the end must be the same. Or, Mr. Dueck likes to say, energy's got to come from somewhere. Can't just magically make it up. As an equation, and this is going to be one of the ones you're going to use actually very often, especially in Physics 12 because it's so useful, we write this. This is the law of conservation of energy. The amount of potential energy before we start, combined with the amount of kinetic energy before we start, or at the beginning, has to equal the amount of potential energy at the end and the amount of kinetic energy at the end. That's if we ignore friction. But we can even include friction now, which normally we can be more accurate. Normally, you've often heard me say, well, we're going to ignore air resistance. We can also have another one. Or potential energy initial plus kinetic energy initial equals potential energy final plus kinetic energy final plus whatever's left over goes into heat. And I just write the word heat. There is a fancy symbol, but I just write the word heat. And that's if we include friction. This is the law of conservation of energy. Justin, a shiver should go down your spine. The lights should flicker. You should hear thunder on the horizon. This is profound. This is profound. Put your pencils down once you've written that down and look up. Type. Skateboard parks are great examples of conservation of energy. Now, the reason they're such nice examples is, accept and continue, this is a yucky curved path. If we were trying to analyze this with vectors, ugh. But energy is a scalar. So for roller coasters, in fact, the phrase I use is there a change in height? Is there a change in speed? Is there a yucky curved path? This is a job for conservation of energy. Show you what I mean. So here's our skateboarder. Doesn't seem very profound. Here's what we're saying. When I put him right here, I've given him some energy. In fact, right now, it's all gravitational potential. That's the total energy in this system. Why is it gravitational potential? Is he moving? No. Now, you're going to see him move. What does the energy turn into? On the way down, all the potential turns into kinetic. And then on the way back up, turns back into potential. This describes how things move. Change height, move. Change height, move. So at the bottom, it's on, well, if I got it right at the bottom, potential would be 0. Kinetic would be maximum. This is why you're the fastest at the bottom of a hill, which you've taken for granted all your life. But here's the physics of why that is the case. But do you notice, is the total amount of energy changing? That's the law of conservation of energy. The amount of energy you had before has to equal the amount of energy you have after. Now, this is a fake simulation because in real life, you do lose energy. You can't just go back and forth in a skateboard bowl. What do you lose energy to? Friction. So I'm going to turn friction on. Just a little bit. Barely any. I'll have my pie chart again, or my bar graph. So there's the total amount of energy. What's the energy slowly being converted into? Heat. See it? That leaves left over. That leaves less left over to get your height back up. And since you can't get your height back up, you're not going to be going as fast at the bottom. That's the law of the universe right there. That's why things run down. That's why things come to a stop, because it's impossible to have a system, Madison, with no friction. This explains everything. This, instead of a skateboard park, think swing sets. When you do an underduck, you're maximizing the potential energy. It's maximum kinetic, which is why you're going nice and fast. But there's some friction between the chains and where you hang on, and you're running into air resistance as a swinger. You're slowly bleeding off energy, and that's why eventually you'll come to a stop. And here's the nice thing. Because energy is a scalar, it doesn't care about what happens in between. Let me turn friction back off. Where will this skater be going the fastest? The very, oh, did he fall off? Did I go too high? Try that again. Okay, and I know we got him glued to the track of this, but you notice he's going at his fastest right here when all of his potential energy has turned into what kind of energy? Turned into what kind of energy? Kinetic energy, motion. Okay? Or, if I reverse the question, when he's at his fastest, how high will he be? At his lowest. Now, I can muck around with this track a little bit. Oh, let's turn friction back on. Oh, didn't have enough to make it over the next hill. But you notice, Jordan, is he on the ground? Oh, some of the energy never got, some of the potential never got converted back into heat or into kinetic. It's just still stored. If a trap door opened up, he would still be able to fall and turn into kinetic until he hit the ground. Is that okay? Reset. Oh, I want this one now. So here I can build my own track. Okay. Is the bottom on the ground? So this time on the bar graph, when he gets to the bottom, there should be a little bit of potential left over. Let's see. Does this ever get quite to the bottom? No. But here is the really nice thing. Because energy is a scalar, I can define 0 to be wherever I want. If we were analyzing this question, we would just pretend that was the ground to give us nicer numbers. This is the law of conservation of energy. Marble energy transfer device. You have wondered why I have this thing behind me. Other great examples of the law of conservation of energy. Spencer, what sport do you play? Bouncing a basketball is a beautiful example of conservation of energy, except there is an outside energy source because you add energy all the time. But if you just bounce a ball, all of the potential turns into kinetic. Now, why doesn't it bounce back to exactly the same height? Do you hear it when it hits the ground? Some of that turned into sound. There's not as much left to go back to, the same way as in the skate park, we saw it being bled off into heat. And there is actually some heat generated as well. The law of conservation of energy. The law of conservation of energy. Swinging a swing set. And the reason this is so nice is you'll notice these are yucky curved paths, but because energy is a scalar, it doesn't care about direction. If I tried analyzing this with velocities or forces, I'd need to know which way it was moving, what direction it was moving. All energy cares about is before and after. The law of conservation of energy. So I've given you lots of cool examples. A projectile is launched straight up into the air. If its initial velocity was 84.3 meters per second, how high does it go? Use energy. We could solve this using D equals VIT plus a half AT squared, VF equals VI plus AT, and VF squared equals VI squared plus 2AD. We totally could. But it says use energy, the law of conservation of energy. Potential initial plus kinetic initial equals potential final plus kinetic final. Plus heat, or does it say ignore friction? Ignore friction, okay. This will probably be one of those equations that you get sick of looking up and just end up memorizing. You don't have to, it is on your formula sheet, but most of you, after doing the homework, will say, oh, potential energy. What was the equation for gravitational potential energy? Turn back a page if you have to. This was Noah's equation. MGH. So I think potential energy initial will be MGH initial. Plus, what was the equation for kinetic energy? A half. So a half mv initial squared, because the mass isn't what's changing, the speed is what's changing. Equals mgh final plus a half mv final squared. Then I always pause and I say to myself, are any of these 0? Specifically, is your initial height 0? Are you starting out on the ground? Noah nods his head. Are we starting out on the ground? Say yes, Noah. So that means, is our initial velocity speed 0? No, it says it's 84.3. I'm not going to cross that out. Is my final height at the top 0? No, that's what it wants me to find. See it? Oh, at the top, How fast are you traveling for a split second? And so what I end up with is this. A half m v initial squared equals mgh final. Mr. Dueck, you didn't tell us the mass. I didn't need to. Why didn't I need to tell you the mass? Is there a mass in everything? Is there an m in everything? Yeah? You know what that means. It's going to cancel. Well, that's kind of cool. What are we trying to find? Which oh, h? How would I get the h by itself? What's next to it? Divide by g. And I get this. The final height is going to be equal to, there's a vi squared, and you said divide by what? Now, there's also in front a 1/2. Look up. Timesing by 1/2 would be like that. I'm not going to put the one. Timesing by 1/2, same as dividing by 2, and that looks cleaner, less scary, because there's no fractions. All right, plug and chug. Noah, you kind of got us started here with potential energy. What's our initial velocity or speed? Read the question carefully. Yeah, by the way, 0 would make the answer 0, which would be... By the way, here's what it's really saying. If that is 0, what's 0 squared? 0. Divided by anything is still 0. Oh, if you're not moving, your height's 0. If you're not moving, you're not getting off the ground. Which, again, seems Captain Obvious, but there's the physics proof as to why that is the case. What did you say, 84.3? Don't forget the squared. 2, oh, Noah, what's G? Yep. Hey, Nick, is there more than one number on the bottom? Yeah. I'm probably going to have to put it in brackets. All of you, please, because I saw on the forces test many calculator errors, try this on your calculator. If you can't get this, it doesn't help that if you can write out the numbers but can't actually crunch the answer. By the way, 84.3, that's about 150 miles an hour. This should go fairly high. You get 363 meters. Now that's ignoring air resistance. Did I do that right, Mr. Dueck? Yeah, okay. What if this projectile only reaches a height of, you know what, I'm going to change this. Put a 1 in front of the 72. 172 meters instead of 363 meters. How much work did air friction do on the way up? Well, you know what we're really talking about? When friction does work, we give that a name. It begins with letter H and rhymes with eat. When I say find how much work any type of friction did, what I'm really saying is take the law of conservation of energy, Kyle, but use the one that had the heat attached. It's going to look like this. PE initial, KE initial, PE equals PE final, KE final. Oh, this time they want me to include heat. Okay. Were any of these 0? Now remember, potential energy is stored energy due to position. It's calculated by mgh. Really, when is potential energy 0? When you are on the... Are we on the ground anywhere here? Are we starting out on the ground? Yep, okay, then I can do this. I could have crossed it out on the next line as well, but Kyle, you can also, okay. Is there, now, are we ending up on the ground? No, at the top, we're at the top. Eventually we're going to end up on the ground, but that's not what this question is asking. Kinetic energy is only 0 if you're stopped. Are we ever stopped in this question? Oh, at the top? Okay. So I have a half m v initial squared m g h final plus heat. What are we trying to find? Heat. How would I get the heat by itself? I think I'd have to minus this whole thing over. Why minus? Because there's a plus. Don't divide, right? I'll get this. A half mv initial squared minus mgh final. That equals the heat. Do the masses cancel this time? Is there an m in every single thing? Natalia's shaking her head. She's correct. There is an m in the first term. Yes. There is an m in the second term. Yes. Is there an m in heat? So the masses don't cancel. So this time, I did need to give you the mass. So over here, let's make a little note. We're going to assume, and I should have put this in the question, and I forgot, m equals 5.0 kilograms. Nice round number. What are we finding? Heat. I got to do that in red for heat. Heat is going to be 0.5. What's m? 5. What's V initial? 84.3 squared. Minus, what's m? 5. 9.8. What height did we actually reach? Not the 363 theoretical, but this time because of air resistance, 172. How many joules, because heat is energy, how many joules of energy did we lose to heat? You get 9,340. If I go to 3 sig figs, which looks like the kind of data they gave me. Okay. Or if I give you a roller coaster, if I tell you how high the first hill is, you guys have seen roller coasters. Second hill, is it going to be higher than the first hill, the same height as the first hill, or lower than the first hill? Why lower? Because you lose some energy to what? Heat. If you barely made it over that second hill, you could actually calculate, or if you knew your speed at the top of the second hill, you can calculate how much you lost to friction. You can start to do roller coaster analysis.